can start now. Welcome to everyone here to our Reimagine session. And for this session, we have, well, it's a pretty specific topic. It's Kubernetes and beyond. And it will be presented by IT Labs' head of technology, yours truly. You all know him, yeah. For all of you online, that's our head of technology with more than 12 years of experience working with software development, all of that stuff. And I'm not gonna keep you waiting. I'm just gonna let Costa take over from here. Costa?
So today we are going to talk about Kubernetes, and it's a real pleasure that I have the opportunity to talk about this platform because I've had some fair experience with it, and I want to share that experience with you all. But I also would like to think about how we should be using this platform, because you know that this is everywhere currently. It's a buzzword in the tech community. And I will try to get first into the principles of Kubernetes. So when we should use it, how we should use it, whether we should use it, because it's not, because Kubernetes it's meant to be used a certain way. So in order to know how to use it, we need to dig deep into the foundations of Kubernetes to see how internally it works, so that we understand better how we can use it in our workloads, in our software, in our infrastructure, in our DevOps principles, whatever we need. Then the second point would be, I will go through some of the traditional use cases of Kubernetes. I will talk about service mesh. I will talk about GitOps. I will talk about databases on Kubernetes. And then the third point will be looking beyond Kubernetes and what kind of innovation are we currently having in this ecosystem, how we can actually benefit from it, learn about it, and be part of it actually. So let's start. Kubernetes principles. So on this slide, we can see some conversation between a developer and a manager. And this actually has happened to me in one of our prospecting calls, when actually, if we run something on containers, even the non-techie guy knows about Kubernetes and talks how we should use Kubernetes. So this is the same picture here with Dilbert. And actually, we just put everything in containers and run it on Kubernetes, right? This is our great savior, our platform that will solve all our problems. So just a bit about me and my story with Kubernetes. This started around 2020. It came out of nowhere on a project where I was working on because it was not in the initial plans. And one of the lead architects on the project decided that we need to move all the workload on Kubernetes, because actually the application that's to be deployed on production needs to be in Kubernetes. So like any good technical lead software developer, I have read a thing or two about Kubernetes, watched some tutorials, written a bunch of YAML files about our two services, which will be running in Kubernetes. So one container for the backend, one container for the API. The database was out of Kubernetes and we deployed it, but then things started to go wrong. I wrote a blog post at that time because I was fascinated by the platform and by its capabilities. And the blog post was named Kubernetes More Than an Orchestration Platform. You can look it up on the IT Labs articles. It talks about Kubernetes as a delivery platform, as an infrastructure layer on top of everything. And I kind of make my opinionated guess there that Kubernetes will be the platform of the future, right? So I wasn't very far from that, but then I did a workshop about Kubernetes Jumpstart for developers back in 2021, I think. And I completely missed the point on that workshop, because I spent time talking about kubectl commands, CLI commands, how to actually run stuff on Kubernetes locally. And I didn't deep dive into the fundamentals and principles of Kubernetes. So I kind of felt that I owe it to the community to actually share and learn more about Kubernetes and then share this knowledge on this session. Hopefully you will have a good time. I have like 20 plus slides on this. I will talk about a lot of stuff. I will deep dive into some of them, and hopefully after this, you will all have a bit better knowledge about the principles of Kubernetes, and then you can start asking the most important question whenever we're trying to bring a platform into our ecosystem, and that is why we should do it and how it internally it works. Back in January, we had a Geek-led DevOps conference we have been following from here from Arena, and like 80% of the topics were about Kubernetes. So it seems like every DevOps engineer currently in the world is using Kubernetes or wants to use Kubernetes or wants to learn Kubernetes, right? So this is a joke in the DevOps community on how it describes actually the fundamental problem with Kubernetes, and that is that a lot of times it is used without knowing the fundamental principles. It is misused. It's not used as it's meant to be used. It's underutilized and complicates accidentally more than it provides value. So the example here, the DevOps engineer, he needs one beer and he spins up 1,000 bartenders. So this is a case very often in Kubernetes where you actually have 2 or 3 containers and you decide to actually run them on Kubernetes, which is an overkill, right? So we need to know how the platform works and what its purpose is before we actually bring it into our ecosystem, because it's a complex platform. It has a lot of steep learning curve, and it can be misused very, very easily. So this accidental complexity is something that comes with Kubernetes out of the box, I would say. So we need to avoid being the DevOps engineer in the tweet there. Before I start with actually explaining about Kubernetes, I want to talk about a concept which you can look it up on Google. It's pretty interesting. It's called the first principle thinking. And it differs a lot from traditional thinking. I don't know if you can see, because it starts with the possibilities and it starts from the fundamental principles. It comes from physics, actually. And it's very hard way to think about stuff. It's really difficult. I have been trying lately, but I can't say that I'm very much successful in it, but it's still to reason not by analogy, by what other people did, based on other people's experience, but to try to learn the basic fundamental principles about a concept or platform, in this case, Kubernetes, to question everything, but to ask yourself, what actually should I question? Because that is the difficult part. And to use the knowledge to make informed decisions, not to be constrained by a particular knowledge. So if you read about Kubernetes and how it's used, you can find a lot of stories on the internet about Kubernetes failures. There is a whole site, I might show it later in the presentation, how people misused it or how actually dangerous it can be to use it on production especially. So to not have this fragile knowledge, we need to deep dive into what actually is Kubernetes, what are the building blocks of Kubernetes, and we will do all this in the first part of the presentation. Then think about what are the opportunities and capabilities of Kubernetes in the second part. And the third part will be what is the current innovation in this ecosystem that's happening. There is a saying that good developers copy, great developers paste, and it's a thing that we all do, not only in code, but with other stuff like whether to choose or not Kubernetes. So even though it's a great platform, as I have said, we need to be very careful about copying other people's use case or other people's solution to a particular problem into our software. So just as a notion, before I start with Kubernetes, this first principle thinking, look it up. It's a great concept and it's really difficult to achieve, but it can provide great value if used correctly. So what is Kubernetes, right? This is the architecture of Kubernetes cluster, and here it has all the main components of a cluster. Kubernetes, I think it's not an orchestration system, because actually it eliminates the need of orchestration. If we think about orchestration, the technical definition of orchestration, is that it's an execution of a defined workflow. So we have first do A, then do B, then do C. Bojan and Maria had a great presentation about durable functions. And there we actually had orchestration and workflows, right? We had first do this, then wait for all of the fan in, fan out to finish, and then do that. So it's a workflow. We can do it in different ways. In Kubernetes, actually, it's not like that. It's not A, then B, then C. It's only A and C. We see the A, which is the current state, and C is the desired state of the system. We need to get from A to C, but we don't care how we get there. We leave to Kubernetes to do that, and that is the beautiful thing about it. So Kubernetes consists of a set of independent, composable control processes that continuously drive the current state towards the desired state. It converges everything towards the desired state. So it shouldn't matter how you get from A to C. So it's not an orchestration system, at least not by definition. So in Kubernetes, a cluster consists of a set of machines. Like here we have the control plane, which can be one machine, or it can be on some of the other nodes. And we have the worker nodes. Each cluster must have at least one worker node. And the worker node actually hosts the application workloads, which in Kubernetes are called pods. We will go through all of the building blocks and the primitive objects in Kubernetes. The control plane is the most important part of Kubernetes. Everything is happening there. This is where the magic actually happens. The control plane components make global decisions about the cluster. So, for example, scheduling, where to schedule the pods on which node, as well as detecting and responding to cluster events. For example, when a pod failed, whether it should bring it up. Control plane components can be run on any machine in the cluster, but for simplicity, setup scripts, when you're setting up Kubernetes cluster, usually everything goes to one machine, just so that everything is close together. So let's go one by one in all of this. The first one is Kube API server, and this is actually the front end of Kubernetes. It is the API of the control plane. It scales horizontally, and it can be accessed to make Kubernetes extensible, and we will see that later. Yes, it's the same slide. Here is the API server. Okay. Okay, no problem. The second part is the etcd, which is the database that Kubernetes uses to store everything that's going on into the cluster. So if we have a process and we need to store something where we are with the process, that goes into the etcd. Next is the Kube scheduler, which watches for newly created pods that have no assigned node and decides which nodes to take and run that container. Kube controller manager is actually running all the controller processes, and all the objects in Kubernetes that we will go through have their own controller process, which actually responds to different cluster events. Cloud controller manager actually doesn't exist if you create Kubernetes locally. It exists in managed Kubernetes services. So EKS or AKS or GKE, so all the Google, AWS, Azure managed Kubernetes services use this cloud controller manager to talk to Kubernetes and to actually use cloud resources and bring them to Kubernetes. So for example, in AKS, when you create a load balancer in Kubernetes, it actually creates load balancer in Azure and talks through this cloud controller manager with Kubernetes. Yeah, that's why I needed mouse. Okay. Next is the nodes. On nodes, we have three things. We have the kubelet, which actually communicates with the Kube API server. And everything that needs to happen inside the node, like run a particular container, it brings it up. The Kube proxy is actually serves as a service layer for the node. And all the communication from the node to the control plane or outside of the cluster goes through the Kube proxy. Container D is the runtime that Kubernetes used to run the containers. This is actually the same runtime that Docker uses. Kubernetes resources. So these are all the primitive resources that Kubernetes uses. The first is the namespace. And the namespace actually provides us with the ability to logically group a set of resources. Some Kubernetes objects cannot be put into namespace, but most of them can be put into namespace. So this is similar to resource group in Azure, when you just logically want to isolate some of your app. The good thing about namespace is that you can actually put resource quotas on it so that it doesn't actually take more memory and CPU. So if you have, for example, an application, you can put everything that that application should have in a namespace, set out the memory and CPU for that namespace, and then the application will never go outside of those boundaries. After the namespace, here we can see the pod, which is actually the main Kubernetes object that runs containers. Usually, we have a one-to-one relationship between pods and containers, but it can happen that in a pod, we can have multiple containers, and we can see some patterns in Kubernetes that actually describe this, like the sidecar pattern. Here, on the left side, we had cron jobs and jobs, which are another Kubernetes objects that we can use. So we can set out jobs in Kubernetes, and we can set cron jobs to run these jobs on some schedule. We can have horizontal autoscaler, horizontal pod autoscaler, so that if we need to have multiple replicas of the pod, this will take care of that. We can have stateful services that, for example, if you want to have a stateful pod instead of stateless, we can use that stateful service, which will be connected to some kind of storage that can be even outside of Kubernetes. So this is if we want to use databases in Kubernetes or Kafka or wherever we need storing, that the etcd, which is the database of Kubernetes, would not satisfy our needs. So we can use storage, we can use persistent volumes and persistent volume claims, which actually gives access to persistent volumes. In Kubernetes, we can have config maps and secrets above. So config maps are actually not secure, and they are for some kind of configuration of the pod. We can put that configuration in a config map resource and use that. If we want to use if we want to save some sensitive data, we can use secrets. And secrets are actually secrets are actually not secret because they are only base 64 encoded. So you should not, I would advise against using secrets in Kubernetes. If you need to use it, you need to have a good role-based access management. So these resources which provided that needs to be set up correctly so that only appropriate people have access to that secret. But this is still hard to manage. So it would be easier to use some kind of managed service like Azure Key Vault and just connect that to Kubernetes and store the secrets there because it's more secure and provides more mechanisms. But if you need to have everything in Kubernetes, people do this, they store stuff in secrets. It's base 64 encoded, but you need to have a good role-based management system inside Kubernetes to set that up. Kubernetes is very opinionated. And one of the things that's discussed in the Kubernetes community is why each pod needs to have a separate IP address. And this is bringing problems for some people that have like 1 million microservices and pods because they actually exhaust all the IP addresses available. And now they have introduced IPv6 to tackle this problem, but still they remain on the position that each pod, each container should have its own IP address. Actually, it's each container, not each pod, sorry. So because each pod has its own IP address, it's a very dynamic environment. Pods can go down, they can die, they can start up, and we have a lot of pods, a lot of IP addresses. So we need some kind of resource to manage all that. And service is that resource that actually stores a route table inside from all the pods and updates that route table constantly as the replica sets and all the other components are actually bringing pods and containers up and down. And this is the replica set and the deployment. I forgot to mention this. This is actually one of the most used Kubernetes primitive resources because it provides the desired state of the cluster. So in my example, when I have been using Kubernetes, I just had 2 deployment files, one from the backend, one for the front end. with one replica inside. And if I had, for example, two replicas, under the hood deployment will use replica set to bring the containers up and running. So the services is actually using endpoints. Endpoints are the IP addresses of each container as they go up and down. It stores a route table to know each time when we access a pod, we can access it by name. So if we have, for example, a backend application, a backend container that has 30 containers running, all of those can be accessed through the service, and service can act also as load balancer. So it can do round robin. You can set affinity on it. So if you want sticky sessions, etc., it's very good to handling the automatic rollout of new containers. So that, for example, Kubernetes provides this out of the box. You have a new version of the container, and in the same time, it can have the old version of the container running and the new version of the container running. And every session that's still running under the old container, which is the old version, until it's cut off, until the socket is cut off, will stay alive. And all the new connections will go to the new version. So this is this automatic rollback. And once everything, all the connections are killed, then everything, then the new version is updated, and we can't see that happening. It's all happening in the background. So it's a really nice feature that gives you out of the box. Ingress is another primitive type that actually provides a layer 7 capabilities. So actually it can do HTTP, HTTPS routing. It can provide probes to actually route traffic. And it had a lot of problems in the first version. So now they are releasing Ingress 2. And a lot of people are actually using service mesh, which we will see later for this purpose. But still, if you are using Ingress, it's a good way to actually have this layer 7 application gateway kind of a behavior. On the upper right corner, we have the limits and quotas. And this is, I have an interesting story about this actually on the project I have been working on, because I wasn't aware of this stuff before, because I haven't been going through the basic principles of Kubernetes. And because the application was deployed in a cluster with a lot of other applications, I didn't set any resource quotas. So resource quotas can be set by requests and limits. For each pod, for each deployment that I'm making, which actually contains pod inside, what is the number of containers I should have? You can define requests and limits. Request is the minimum amount of memory and the minimum amount of CPU that I will need to get the container up and running. And limit is actually how is the maximum that I can take. What is the maximum that I can take of CPU and limit? And if you don't set this out, and if you have some intensive input-output operation, then you might bring the node down. And this is what happened actually on production, unfortunately, because I haven't set this up, and no one actually bothered to review that appropriately. So this is a really powerful feature. You can actually measure what is the limit that you should actually measure what is the minimum amount of resources that you will need and what is the maximum amount of resources that you will need before you actually go to Kubernetes. This is a really important concept that that you need to be careful about. And up to the right, we have the node and custom resource definition. So this is just this is a way to actually extend the Kubernetes API, which we will see later on. Okay, so let's talk about the game changer ability of Kubernetes, at least in my opinion. So in the next slide, we will look this under the hood in more details, but actually this is what's actually happening in order to get from current state to a desired state, which was requested by an API, by us or by anyone. So Kubernetes defines the application runtime lifecycle as a couple of resource types, such as deployments, right? So in deployment, I can tell how much replicas do I want of a certain container. and I can update the version of a container. Kubernetes API server exposes a suite of declarative APIs for resources as a centric entry point for submitting and modifying the desired status of specific resources. And we have a thing called event queues inside. So this works kind of similar with Azure Durable Functions, as we have already presentation about that. And it puts everything into etcd, which is the database of Kubernetes, and event queues as the process go from the current state to the desired state. The controller, actually the main point in the control plane of Kubernetes, reconciles, and it has an infinite loop, control loop, that goes infinitely, and just takes care about getting from A to C. So on the next slide, we can actually see this flow and we can start explaining it. So let's say we have a deployment object that we have written in a YAML file, right? And this is the first step. And we are calling the API server, which tells us you need to have a backend service with 2 replicas. Then the API server creates a deployment into the etcd, into the database of Kubernetes, right? And the deployment event queue sends to the deployment controller that the deployment is created, and it is required that the backend service needs to have 2 containers. Then the deployment, as we have said, under the hood works with replica set, sends an event to the replica set that we need 2 containers of the backend service. Then the replica set contacts the etcd and stores that information in the etcd, because we need to have storage to actually track the progress of the flow. Then the replica set controller goes to the pod event queue and says create pod. Create pod creates a pod into etcd. So this is kind of similar, right? And then the pod binding event queue starts, and this is where actually we go outside of the control plane. So this is the control plane. This is the node where the container is running. Pod binding event queue creates the binding in the database. And once the binding is in the database is created, an event is set to the kubelet, which is running on the worker nodes, that we need to create 2 containers. In our case, this is just with 1 container. Or we need to update a container, right? And this is where the automatic rollout of the process goes on. Then after the containers are updated, the process is not finished, because we need to notify the deployment that we are in the desired state. If we don't do that, he will try again and try again and try again. So it will be stuck in this crash loop back of error that you are getting when the container is not running properly. So after the container is successfully running, then we need to send information back to the pod event queue that everything is okay, that we have created 1 pod or 2 pods. It will send 2 events. Then the pod event queue will go and update the replica set and says, you have said that I need to run 2 containers. 2 containers are running. The replica set will get updated that the desired state is satisfied, and then the replica set will update the deployment that everything is fine. And this is where Kubernetes will actually calm down and say, okay, we're good. We don't need to do anything here. This is this self-healing ability of Kubernetes. So if for whatever reason a container is down, the control loop will pick that up and will go through the process again, because it has an infinite loop inside, a control loop that's running all the time, and it's converging your current infrastructure, your current requests to what is actually out there. If it's not satisfied, it will just keep going on and on. So this is similar to the human body, if you think about it, right? This self-healing ability. But it can also be very dangerous, because if we make 1 mistake and we have some kind of continuous delivery process, someone didn't check that appropriately, we have GitOps or whatever the new notions are, we can come into a situation where this self-healing ability will actually kill the cluster or kill the nodes or kill all the containers, just like autoimmune disease in the human body. So I make this parallel here, and we have a lot of cases where this can actually happen. So I don't have the mouse. Probably I should go to the side, right? Or it's the other side. Yeah, there it is. Okay. So if we go to the Kubernetes failure stories, we can actually, there is a site and there is quite a few of them. The last one being in 2021, which is kind of satisfying. So probably in 2022, everything is resolved, right? So this is a case where this is a post-mortem, and a lot of these are post-mortems about different ways to blow up your Kubernetes from Airbnb or from other cases. But this is one of the most interesting because the self-healing ability actually did this. So this is the commit that actually brought down, oh, sorry. Yeah. Okay, so this is the actual site. And this is the actual commit that did all the errors. So when you are working with YAML files, you can work with parent-child, so you can have some kind of parent where you will define some stuff that you want to have in all the other YAML files in your Kubernetes manifest. So not to brag about that, but this was in their most parent root file that they had. So they did this small change, and they had Argo CD and GitOps setup and everything. And this deployed to Kubernetes, but because they didn't have these parentheses there, it looked like they are deploying empty manifest files. And that actually told Kubernetes, if we go back to the previous slide, that we need to kill everything. That now the desired state is that we don't need anything. So the story is that 478 services were deleted on production immediately before they actually figure it out. And this is the self-healing ability, this desire to actually satisfy our needs all the time in an infinite loop. This is what is the game changer ability, but also this is what makes Kubernetes dangerous, and we need to be very careful what we are doing. The same was with the previous story I had about resource quotas. If we don't set them out correctly, it can bring the nodes down, it can consume a lot of the CPU and memory and decrease the performance of other services if we have multiple applications in Kubernetes. So we need to be really careful with this. So let me just try to find my mouse again. Okay. And let's continue with the next presentation. Next slide. So Kubernetes has this concept of custom resource definitions and operators, and this is the ability to extend the Kubernetes API with custom resource definitions. It allows you to instruct Kubernetes to manage more than just containers, and operators come here into play, and this is a way to extend Kubernetes. Operators use these custom resource definitions. They are watching them, and they are changing events, communicating with the Kubernetes API, and under the hood, they are still using pods, services, all the primitive types of Kubernetes. But if you are, for example, Kafka or MySQL or whatever application out there software, and you want to run natively on Kubernetes, you need to create operators. And you do this by creating custom resource definitions and operators to work with those custom resource definitions. Operators actually allow for automatic implementation of these day one and day two tasks in DevOps. So day one tasks in DevOps are installation, configuration, etc. And day two tasks are reconfiguration, upgrade, backup, failover, recovery. So all of that is handled by an operator. You just install it through a Helm chart. I don't know if you have been to Vladimir Trachev's presentation about Helm, but actually it's a package manager for Kubernetes. Just install a package with a bunch of pods, services inside, and you are up and running. You have an up and running Prometheus in Kubernetes, or up and running MySQL or Kafka or whatever you need. And this is why they are called native Kubernetes applications, because they work natively with the Kubernetes primitive objects. Kubernetes operators are actually controllers for packaging, managing, and deploying the application. So all these day one and day two tasks in DevOps. And in order to do these things, the operator uses custom resource definitions that you as a developer define. So you can have your own operator if you are running some kind of software that others can benefit on Kubernetes. And the operator's job role is the same as the ones with controllers we have seen previously with primitive types. So it's to reconcile the actual state to the desired state using the custom resources now. So this is how Kubernetes can be extended whatever we need. And operators are declarative rather than imperative tool because you actually declare what you need. And there are a lot of operators that you can find. I have mentioned some examples, so Prometheus, Postgre, and you can have a Postgre high availability database cluster running as an operator in Kubernetes. Elasticsearch, Kafka, MySQL, Cert Manager. This is what we have used for our project actually to manage the certificates of the front end and the back end containers. So it uses, I don't know what was the name. It uses encrypt or whatever the name was of the certificate operator manager, and each 3 months you get automatic renewal of certificates. So this is very easily to do in Kubernetes. You just install an operator called certificate manager and you use it to set its custom resource definition in Kubernetes to achieve this. There are actually hubs for this. So I can quickly show you this. Okay. So this is the artifact hub. Let me just go back. Packages. Here we can see a lot of familiar faces, like Ingress Nginx or Prometheus Stack or Certification Manager or Redis or Argo CD for DevOps. We'll take a look at this. Kubernetes dashboard, Grafana, Postgre, Jenkins, everything can be found here as an operator. In order to build operator, there are actually frameworks that can help you with that, like an operator framework or Kube Builder. You can use them to build your own operator if you're having some kind of software that you want to give it to the community. And one very nice and popular operator lately is Crossplane, which we will go through in the next slides. So this is the first part of Kubernetes, which is actually the traditional, the primitive types and going through what Kubernetes is and what it does under the hood. Next, we will try to go through beyond some of the traditional use cases. But before we go to that, I would like to go through the Kubernetes design patterns. And this is inspired from Django 4 design patterns we have in programming. So we have foundational, structural, behavioral, higher level design patterns, like groups of design patterns. And when we are designing cloud native applications, we need to take this into consideration and to know these patterns just so that we can have a better Kubernetes workloads. So if you plan to migrate to Kubernetes, to use Kubernetes, I would strongly advise to go through this and think about your applications and how you are actually building them to make that little bit of compromises in order for them to run on Kubernetes better. So the first one is health probe. And this design pattern dictates that every container should implement specific APIs to help the platform observe and manage the application in the healthiest way possible. This means that if you have a .NET API or Java API, you need to have a health check API point, and you need to connect that to Kubernetes. So in order for Kubernetes to know whether your application is healthy. If you don't have this, then Kubernetes will assume that it's not healthy by its own standards. So they have their own standards how to do that. But if you have a health probe and a health API to provide to Kubernetes, this will be your benefit, and you will actually tell Kubernetes when the application is healthy. So if you have some integration, you can put that in the health probe. If you have a database, you can test if the database connection is alive, because if it's not alive, then the container is not healthy, and the Kubernetes will not know that it's not healthy, right? So to be fully automatable, a cloud native application must have a high observability, and this is achieved with health probes. The second pattern is predictable demands. And this explains that every container should declare its resource profile and stay confined to the indicated resource requirements. And this is what I did wrong in my case. I I didn't predict the demands. I didn't test it out that we might have a lot of bigger transactions and more memory and CPU intensive. It was memory in my case, behavior on production. So I need to predict what the demands will be, and we can do that before we actually go to Kubernetes. We can test it out. We can write an architecture fitness function to actually check out the demands, whether we are in the boundary of request and limits, and then we can deploy to Kubernetes. Declaring the requirements is essential for Kubernetes to find the right place of your containers within its ecosystem, its nodes. Because if you don't have that, it will place maybe on some node that has not that much memory and CPU, and you will have decreased performance. Automated placement is an interesting one because it explains how to influence your workload distribution in a multi-node cluster. So there are ways to actually influence where your application, where your containers will be running. So if you know the Kubernetes cluster, you know the nodes there, you can actually instruct Kubernetes in a declarative way because everything is declarative here. You can instruct, I want to run on these nodes because these nodes are the ones with greater CPU and memory, and I will need that. Or these nodes have something that other nodes doesn't have. So you can actually automate the placement of the container within Kubernetes. And these are the foundational design patterns. The structural, we start with the init container. And this is actually to have in the pod a separate container that will initialize all those initialize related tasks to separate from the main application. So this enables separation of concerns by providing a separate lifecycle to init processes. And this is very recommended in Kubernetes to actually have the init logic be in a separate container in order to be fully cloud native, right? Sidecar is the next one. And Sidecar is very interesting because it describes how to extend and enhance the functionality of a pre-existing container without changing it. So all those stuff like configuration, security, communication can be put in the Sidecar container while your application is running in the real container in the same pod, right? And this is what the service mesh is all about. We will look at Istio later on. Next are the behavioral design patterns. The first one is bad job, and this actually describes how if you have some kind of very long-running intensive workload, you need to separate it out and run in an isolated and atomic fashion until completion. So in a distributed environment, this is very important. If you have some kind of long-running workflow, you need to make little chunks of it on Kubernetes. You can't have one pod running everything. That's why transactions are not well suited here because they consume a lot of memory. This was my case when I didn't put the resource quotas. Actually, it was a transaction with database which took a lot of the memory resources and brought the node down with all the other applications. Stateful service. It describes how to create and manage distributed stateful applications with Kubernetes. And this is applications where we actually need to persist something, an identity, storage, and also it has an ordinality, so you can actually order stuff. This is why stateful set are used by Kafka, because in streaming, the order is very important. And stateful set primitives, which we have seen, the primitive object type actually provides this out of the box. Service discovery is another one, and this is how the clients can access and discover all the instances within Kubernetes. And Kubernetes provides multiple mechanisms, as we have seen, services, which has the route table of the container IP addresses as they go up and down. It has ingress to handle the layer 7 access to the cluster, but it also has service mesh, custom resource definition operators like Istio or Linker that can be used that also have this service discovery embedded into them. Higher level are two, controller and operator. Controller is the one that is the actual Kubernetes main controller that has all the replicas, deployment controllers inside, and it's the heart of Kubernetes, and it reconciles the current state to the desired state, as we have discussed. And operator, we have already been through this. It uses the CRD, the custom resource definition, to encapsulate any operational knowledge inside Kubernetes. there is an increasing number of operators, and this pattern is actually turning to be one of the major benefits of Kubernetes, and one of the, I see it as the future of Kubernetes. We will see more and more operators coming into this ecosystem. Next, we have the use case of database on Kubernetes. And this is very important to know, because Kubernetes is very dynamic environment. It's not meant to serve stateful applications, at least not, that's my opinion. So when it comes to having database inside Kubernetes, you need to have, as you can see here, a persistent volume claim for each database instance. So here we have 3 instances of Cassandra in this case, all of them in the same stateful set, STS. We have a service accessing them and doing round robin, some load balancing. We have persistent volume claims for each database, and then we have a persistent volume which communicates outside of the cluster with an Azure storage or S3 or whatever we are saving the data in. Because we need to be careful to not lose the data. That's why we need this storage provider at the end. If we don't have this, if we store it on volumes, then if we upgrade Kubernetes, we will likely lose the data. So unlike stateless applications, you can't just redeploy a clean container image. So that is the main issue with stateful in Kubernetes. Another consideration is that any database deployed in Kubernetes has a high chance of database application restarts and failovers. It's a dynamic environment. It does this all the time, whether it's self-healing or some other reason. So it can be stressful due to all the reasons. You need to take care about replication, or if you have sharding, for example, you're separating the data, how you will do that here. Failover, scalability, etc. So my advice at this point of time would be to explore other options. So there is nothing wrong to use AWS RDS and just connect to that database from Kubernetes cluster, or use Azure SQL database. Unless it's a requirement from the client, you don't need to put your database in Kubernetes. However, as we have seen, operators are coming strong, and we have operators for everything now, for MySQL, for Postgre, for everything. And this can actually solve the problem. So a lot of the blog posts now from Kubernetes Expert is that maybe it's not that bad of a case to put your database in Kubernetes. So at the end of the day, it will come to how much fault tolerance can your business have. It's up to you to decide whether you would use some operator which handles all this stuff. So you have high availability Postgre cluster that you can bring inside Kubernetes cluster. But it will be up to you. I would say at this point of time, it's still not mature enough, even though there are operators, and you should explore other options and putting your database and data in a managed service on the cloud or on-prem if that is something that's a requirement. Next is service mesh. And I will talk about Istio here, but before we talk about Istio, we need to go through what service mesh is and why it's used. So service mesh as a need came from the challenges with microservice architecture. So when we are setting up a microservice, each microservice has its own bounded context and logic, and we need to take care about a lot of the non-business related things, like how would those services communicate between each other? Should we have some kind of certificates for these services? How we would measure logging and how we would take telemetry? How would the retry logic be for all of these microservices? How will the security be handled? So all of this, we have one way to go, and that is not use a service mesh and actually code this inside our microservice. So here a microservice, and for each microservice, we have this set of standards. We need to have this kind of security, these certificates, this is how we do discovery, and this we do that for all microservices. But a time passes and you find a new, better way to do logging, for example. And instead of going to each microservice and changing that, you can use a service mesh to actually update all that at once. So as you can see on the architecture here, we have a control plane above and data plane below. This is actually the Istio architecture. And on the control plane, we actually have Pilot, Citadel, and Mixer. And in the newer versions of Istio, this is not the case anymore. So Istio is an operator in Kubernetes, just like Prometheus, whatever we have seen before. And you can install it through a Helm package. Install Istio and we have it. Istio runs with several pods, which are primitive Kubernetes types. And it can be used to upgrade all of this non-business related stuff at once. So it has a network layer for communication. It can do traffic splitting. The proxies that it uses are Envoy. So on each pod that we have, so for example, this is some front end, this is some backend container inside the pod. For each pod, it automatically runs another sidecar pod. This is the sidecar pattern that we have discussed. And this is the actual proxy from which Istio, from the control plane, communicates with each of the pods. So if you have 1 million pods, and if you want to change the way you do logging, you can do that through a service mesh with just one update. It stores in the control plane all the sidecar proxies and it updates them instantly. And this is the beautiful thing about service mesh when we have this microservice architecture. So you don't have to adjust any deployments, any services, anything. You just have the Istio configuration, which is separated, and you have all the traffic routing, retry rules, timeouts, everything defined there, and update them across all your microservices. So this is a way to set up standards for your microservice architecture. You can have the same configuration, the same security across all your microservices. You don't need to code that out inside each microservice. So everything is pushed from the control plane to the sidecar proxies. Also, Istio can get metrics and tracing data from all these Envoy proxies, which are containers running inside the pods of each of your microservice. And Envoy proxy is very good implementation that Istio uses because it has a very small footprint. It's written in C++. It's very fast, and it would not enlarge your memory footprint by much. And all the tracing gets back to the Istio control plane, as you can see. And you can use something like Prometheus then to actually monitor all of that at once. Also, Istio can serve as a gateway point to your cluster. So you can set up your rules, traffic, everything before the cluster, before you enter the cluster. And this is a better way of using and handling connectivity in Kubernetes instead of using something like Ingress, which proves to have a lot of problems. This is another concept that goes beyond the traditional Kubernetes use cases, and this is infrastructure as data. Now, I know a lot of you have heard about infrastructure as code, and this is the standard nowadays, but according to a cloud native point of view, we need to have infrastructure as data, not as code. So cloud-based infrastructure should have 3 properties. It should be ephemeral, which means that it should be short-lived. It should be recreated anytime we need it. We should not be afraid to recreate it. It should be simple, and it should be versioned. So if you want to provision and manage your infrastructure, you can use something like JSON file that's used in ARN templates, or YAML files, which are used in the other infrastructure as code, which we will go through in this slide. But why do we need to write code for infrastructure? So treating infrastructure as code can open the door for technical debt. This is the actual belief in the Kubernetes community. That's why we shouldn't use infrastructure as code. It also leads to unnecessary complexity. Why do we need to manage the code, to manage a whole bunch of code to define our infrastructure, when all we need is to describe it? So if we go to the popular infrastructure as code tools that we use, the first to mind comes Terraform, right? It uses their own language, HCL, which is JSON-like. It's platform agnostic, so it can deploy anywhere, like any cloud provider, which is public or on-prem, bare metal, anything. and relies on these JSON state files to keep track of the infrastructure that it created. So this is like a structured file log, right? So you have your JSON state and you deploy there. But Terraform also has some loops and conditions, and you can modelize all that, and you can have a new version, and then you need to refactor that. So it's a code at the end of the day. It's not just a definition of the infrastructure. It's more like coding your infrastructure. And whenever you write code, you will have problems. So less code is better, and no code is the best. But unfortunately, we gotta have some code, right? So Pulimi is the next big player in infrastructure as code. It has the same concepts as Terraform. It also has a state file. And the major difference is that instead of using this HCL language that you need to learn if you want to use Terraform, you can use something like C# or Python to write your infrastructure. So it's better in that way, in my opinion. Ansible is the next that started out as configuration management tool. And this uses YAML to define infrastructure, and it's stateless. And the new player here in this world is Crossplane, which is actually an operator in Kubernetes, a cloud agnostic tool that runs on Kubernetes, and it's used to provision cloud resources outside of Kubernetes. So it's really interesting. You can actually tell Kubernetes to create an SQL database on Azure or RDS on AWS. And the operator goes, connects to the account, and creates it. It's Kubernetes native also. It is declarative because the API is declarative. You just tell, I need a new database on AWS, and Crossplane takes care of all of that. It has a custom resource definition for all the major cloud providers, and it can be used. So of all of these four that I have mentioned, Terraform, Pulimi, Ansible, and Crossplane, only Ansible and Crossplane are actually doing infrastructure as data, right? Because they don't have state files, they don't have code, they just define the infrastructure. It's a declarative approach to infrastructure, which is more close to the cloud native world and to how Kubernetes is opinionated and how we should make our applications to be best for Kubernetes, best fit for Kubernetes. So because Crossplane runs on Kubernetes, this is actually interesting. It uses the etcd database to store the state. So it's kind of not that infrastructure as data if you think about it. Maybe Ansible is the only one. But still, the idea with this is that we shouldn't introduce any technical depth when defining infrastructure. It's just a definition. It shouldn't have any for loops on variables or anything. Although it is good from our programming perspective to have variables and just reuse stuff. But then when we are doing this, we are actually having problems. So the best way is to have less code and if possible, no code at all. That would be the best. Next of the hot topics in Kubernetes world is GitOps. And this is where I have an example of Argo CD, which is probably the most popular operator on Kubernetes, which actually does GitOps. GitOps is a practice that uses Git repository as the single source of truth. So everything is in Git. Any change you want to do to your infrastructure, to your configuration, to your application, anything needs to go through Git. All the auditing is there on Git. All the role-based access management is done on Git. And whatever tools you are using, GitHub or GitOps or Azure repos, whatever, everything is in Git. Everything starts there, and you are not allowed to do any kind of modification on the right. Everything is handled through this guy here. So when we commit code to Git and push the image to some kind of image repository, we also update values, and this is a separate repository in this example. It doesn't have to be a separate repository. It can be the same. And Argo CD, continuous deployment, actually has a webhook sync with that repository. And whenever we do change, Argo takes that change and syncs the manifest, the YAML, the desired state to our Kubernetes. And it can work with multiple environments, multiple clusters. Here we have 3 clusters, test, end-to-end, and release. So teams commit declarative configurations into Git. And these configurations are used to create environments needed for the continuous delivery process. There is no manual setup of environments, anything. If you need to spin up new environment, you do a commit code. If you need to do an application update, you do a commit to Git. So everything starts there and everything is the single source of truth. You shouldn't be allowed to go to AWS console and to update anything. That should be forbidden for everybody in a GitOps scenario. So you need to go and commit the code, have a pull request, have it review, have the auditing there, who did what change in order to have better tracking on postmortems or anything. So it's a very good practice if you are able to achieve it. So Argo CD is a Kubernetes native cloud deployment tool operator, and it uses unlike other continuous delivery tools that only enable push-based deployments like Octopus or whatever you have used. This actually has the pull mechanism. So pull updates from Git and deploys them directly to Kubernetes resources. It enables developers to manage both infrastructure, configuration, application updates, everything in one system. Operates in its own namespace within the Kubernetes cluster. So you can, after you deploy the operator, you can find it, you can see how it works. And offers a very powerful command interface and also a web-based UI if you want to watch the workflow, if you want to communicate somehow with Argo CD. It has strong support for multiple teams because you can restrict the custom resource definitions this operator uses to only a particular team. And you can say, for example, the dev team from, I don't know, India has only access to this test environment. So you can have multiple teams working with it. Best practices when using Argo CD is to separate the source code from the configuration repositories. So you can set that up to multiple repositories. You can have one repository for configuration only, one for application code, one for the infrastructure as data. And this is one of the most recommended way to use it. And also we need to test to test the manifest before we do the commit. And there is a way to do that with Argo CD. Next, I will try to go through briefly, I know that's been 1 hour, to what is the current innovation in Kubernetes beside the custom resource definitions and the operators. So the future is in the CRDs and operators, abstractions which we build on top of Kubernetes and make available to users through the hubs and everything. And this is kind of reminds me of the Linux distribution era, where actually we had different distributions of Linux, right? And all of them were on top of the Linux kernel. Now everything is on top of Kubernetes with all these primitive resources that we have talked about. And we can just put everything on top. It has a great API to communicate with it. And it has this declarative way of doing things, which is declare what you like, and Kubernetes or the operator running on Kubernetes will take care of it automatically. So a lot of automation. If we can look at the landscape of the cloud native foundation, which is where Kubernetes actually is. There it is. We can see a lot of things going on here. So we can see service proxies, API gateways, service mesh like Linkert and Istio, scheduling and orchestration. There is cross-plane, databases, streaming and messaging. So basically everything, you can find everything here. And if you don't know how to use this, there is a guide actually, because there is a lot of small squares and it's difficult to get your way around this. So if you go through the guide, you will see what is the cloud native landscape and how you should use it if you want to find something that's not out there. Okay. So the future of Kubernetes, if we go back in time and see how we started with imperative configuration when we were using. I haven't been using, but the people have been using in the 90s, scripting, bash, Pulimi, and everything to get your infrastructure up and running and configuration up and running. We moved to a declarative configuration, to configuration management and provisioning in 2020 with infrastructure as code. And now in 2020 with tools and operators like Crossplane, we actually have a declarative API, self-service, and full automation of everything that's needed. So just a bit about Crossplane on this slide. It's a modern API plane, infrastructure automation platform built on top of Kubernetes. And it matches all the attributes for the next evolution of infrastructure engineering, in my opinion. It uses custom resource definition, which is a Kubernetes extension point. And we can assemble infrastructure and services from any cloud and service provider in Kubernetes. So Crossplane actually allows us to compose these APIs in a no-code way, just with a simple YAML configuration. This is very good for large organizations, and we had a talk like this recently about how they are using this for platform engineering. So if you have a large company and a lot of people are coming to you with different requests, you can build your own platform application, platform infrastructure that will actually handle those requests automatically using a thing like Crossplane to actually provision everything through Kubernetes. So instead of building a pipeline where someone would define that, for example, a developer needs to test out how some machine learning service is working, or how some new way of database is working on or how some analytical tool is working on Azure. He can do that in a declarative way. So you can build a UI where he can just select what kind of services from what kind of provider it needs. And you can use Crossplane then to actually provision those resources on the public cloud providers out of the box. So it's very easy. It doesn't have a lot to it. You can just go through the documentation and see how it works and how it actually brings provisioning public cloud infrastructure from Kubernetes, which is very interesting. The last thing I want to talk about is WebAssembly as the latest innovation in the container world. So this is a tweet from 2019 from Solomon Hykes, which is actually the founder of Docker, which says that if WebAssembly and WebAssembly interface existed in 2008, we wouldn't have need to create Docker. That's how important it is. So if we ask ourselves, why do we talk about WebAssembly in a Kubernetes presentation? It is because WebAssembly is no longer only in the browser. It's outside of the browser as well. And if we look at the workloads and how we did things before the cloud, after the cloud with containers and Kubernetes, right? When we have Linux and Windows containers, the new way of doing things now, and probably a better way, is using WebAssembly. So the original intentions of WebAssembly was to solve performance problems for JavaScript in the browser. So the goal was to achieve local native application speed in the browser. And you can't do that with JavaScript because it runs with something like a V8 engine, and it has a lot of performance. It can have a lot of performance issues. So the idea was how we can use a high-level language like C# or Java, or maybe a C++, write an application, compile it natively to a WebAssembly, and then deploy it to the browser. And this is the original intention of WebAssembly. And many programming languages can compile their applications into the WebAssembly target code so they can run in the browser. And this decouples application development from runtime, because you actually have the runtime in a different language, which is the WebAssembly in this case. And this can greatly improve code reusability, but also it provides a secure, portable, and very efficient sandbox that can run applications securely anywhere on the internet. So it's widely supported by all mainstream browsers currently, like Google Chrome, Edge, Firefox. And in March 2009, that's why the tweet was in 2009, Mozilla launched a WebAssembly system interface, WASI, to standardize the interaction between the WebAssembly application and system resources like file system, memory management, thread management, network connections, everything that's file-based. So actually it took out the concept of WebAssembly out of the browser that can be used anywhere. And due to its high security, portability, efficiency, and lightweight features, it is ideal for application sandbox scenarios. It's even more secure than containers, because containers contain the libs, the libraries. So whenever you do a Docker container, you start with from .NET image or from, right? So it contains the libraries. It has a much larger footprint than WebAssembly, because WebAssembly only contains the application. It compiles it natively to run natively. And when this happened, WebAssembly received extensive attention in the community of containers, function compute community, and also IoT community, because it has a very small footprint, and it can be running on edge devices. So WASM plus WASI became actually a standard, and now I think 1 month ago, Docker announced that they have a beta version of WebAssembly containers, which means that if you use Docker Desktop and just allow beta features, you can actually run WebAssembly containers and see their power, their efficiency, their small footprint. There's actually no cold start with that. So I had discussion actually with Martin about Quarkus and how it builds actually native images. And this is actually how they tackle now the cold start problem, because you no longer have the libraries doing all the cold stuff. You have only the application code. And this is, I think, the biggest innovation coming into Kubernetes now, because Docker will support WebAssembly, which means Kubernetes will support WebAssembly, and you will be able to run WebAssembly containers. They have a lot of advantages over Linux containers, which are most used, right? They have higher performance. They have smaller footprint. There is even a WebAssembly Edge open container standard that you can use for edge devices, for IoT. So it has also a very good case in IoT, where the edge devices have very limited resources, and Linux containers can be too heavy for them because they contain the application. So we're just going from bigger to smaller all the time. I don't know what's next, probably no code. The application of WebAssembly can be 1% of the size of a similar Linux container application. You can compare that. So you can have a .NET image running a simple API, .NET container, running as Linux container, and compare the size of the image with the size of if it's built as WebAssembly container. You will be surprised how small footprint it has and how fast it runs and how secure it is, because it's in a separate sandbox. So it outperforms Linux containers by a mile. So we have a use case here as well that I think 2 weeks ago, Adobe started running 90% of their container compute as WebAssembly. They are currently in the process. They are writing about it, so you can follow how they do it, but they want to run everything as WebAssembly. So let's see how that goes. But I think it's a very important feature that comes into Docker, and we need to notice it, to know it. So to end it all, Kubernetes is a platform for building other platforms, like we have seen with the operators and the custom resource definitions. And it's a better place to start. It's not the end game. We need to, if we go to takeaways, so Kubernetes is here to stay because a lot of the things are running on Kubernetes currently. Even the cloud providers are using it under the hood in a lot of their services. So knowledge about Kubernetes is here to stay. But if I talk to a developer audience, I think that you would not need to know everything about Kubernetes from an admin standpoint. You need to learn about the basics and the fundamentals in order to answer the question, why do I need it? Not to jump into implementation immediately. So forget about what other people did, the other use cases, learn the fundamentals, isolate it from your use case, and then think whether Kubernetes is fit for you. Because if you order one beer, then you don't have a use case for Kubernetes. But it's here to stay, and it's good to follow what's going on in that ecosystem. So learn the principles about Kubernetes, first principle thinking, learn them isolated, and that's it. Kubernetes is going from container orchestration. It has never actually been an orchestration, but it's going from that notion to more of a control plane where we have a declarative way of doing stuff. So with GitOps, with service mesh, we can just have a declarative way of doing things with infrastructure as data. Just we want this, and we have the automation do everything for us. So it is going in this direction, and it will keep going in this direction in the future. Think twice before running databases or any stateful services inside Kubernetes. It's very difficult to manage. It's a very dynamic environment. So I would actually advise you to think twice before running it inside Kubernetes and explore other options. And last, that a lot of innovation is happening in the Kubernetes ecosystem with cross-plane operator and the WebAssembly we have seen at the end and how it will actually change stuff. So keep track of it and stay informed to make informed decisions and not be constrained by knowledge. And that's about it. I think it was on time. So thank you all for listening. Now we can go with questions. Marco? No questions? Anyone? Go ahead.
How safe do you find this way of platform building in the light of the latest situation in Ukraine? Because there were some other which were using cloud and web storing, and the data was leaked into an unknown direction, actually on the other side of the war, so to speak.
Well, Kubernetes is a platform. Are we talking about Kubernetes or we're talking about security in general?
About Kubernetes, cloud is currently not considered to be a very secure way to go. But anyway, for example, Rashkovsky, the system that actually executed from the Russians, and there were some other citizens in Europe that also did the same, but they figure out what it is about, but not in Ukraine. And when Russia was invading Ukraine, they used this. Like they could see, for example, the tank is on the street, you know, because in the traffic lights they have these cameras, and then they can leak the visual
right.
segment.
And this happened because I'm not familiar with the use case. This happened because there was a breach of security on the cloud, right?
Yes, because through it they can leak it, and actually the guy that was working for the government, he's a professor here at the university, and I think he was undoubtedly aware. He's double PhD, so he's very much into computer programming. And
yeah, but you know, when you're actually using cloud, there is this concept of shared responsibility, and you are upfront giving up of some of the things you can manage on your own. So if you have your own cluster and manage everything on your own, you can have network engineers, security engineers work for you and set up everything up to the latest standard, keep everything up, and you have control of everything that's going on. You can detect maybe errors more easily, but the whole responsibility of handling security is on your back, right? But when you're using cloud, there is this concept of shared responsibility when a lot of the times when we're using managed services, we
actually tell the cloud and trust the cloud to do the best job it can. And if a security breach happened, then if it's the cloud fault, then the cloud failed in this shared responsibility model. And we can see this trend recently with a lot of companies moving away from cloud and trying to actually build their own data centers and handle everything on their own. And Kubernetes is a great platform for that, actually, because it provides a lot of the automation abilities out of the box, and you can use it to automate your workloads, to use operators or everything, to set up security. And it is a trend. We will see how it will go. Also, the costs, you can regulate more when you are doing your own hardware and you're doing everything on your own, but still you will have to pay security network engineers in that case. So it depends on the use case. I would say if you are a big company, you should run your own servers, right? Like I think Meta is running their own data centers. They are not actually using AWS or Azure or anything. They manage everything on their own, but they have the resources to do that. And if you have the resources, maybe that's the best. You will know, you will learn, instead of just trusting the cloud and clicking on a portal and everything spins up automatically. And it's magic, but that magic has its price. Any other questions, maybe online? Folks, thank you for participating.